Greetings and welcome back. This is N1IR. This is part 10, weak signal propagation. Let's begin. Okay, we're on weak signal propagation. Next is going to be these sections. Alright, so basically we have 5 layers of the ionosphere: D, E, F, F1, and F2. Now, why did they start at D? Because they originally thought there might have been more layers between the Earth and layer D, but that wasn't the case. So, during the daytime, layer D, E, F, F1, and F2 are separate. During nighttime, those layers kind of shrink and all combine into the F layer and F1 layer. They just combine and become F. D and E disappears at night. And that's because of the sun. The ultraviolet radiation from the sun increases activity in the ionosphere. The usual name for electromagnetic waves that travel through space are radio waves. So here's our transmitter. If we're transmitting on a frequency, we have a combination of space wave, which carries straight direct out, sky wave, which bounces off the ionosphere, ground wave, which hugs the Earth, the curvature of the Earth. We have a skip zone, and we have skip distance. The skip zone is between the end of the ground wave to the next sky wave. HF bounces off the ionosphere. VHF and UHF pass through. So VHF, UHF is what we call line of sight. HF tends to bounce off the ionosphere. And you can observe the differences between the different frequencies. 2 meters tends to go straight through. 6 meters is kind of one of those weird bands where it could do either or. It can either bounce off the ionosphere or go straight through it, depending on how the ionosphere is charged. 40 meters, you have a short skip distance. Then we have 20 through 14, 20 meters, 14 megahertz, which has a little bit longer skip. And then we have 10 meters, which is 28 megahertz, which is even longer. So as frequency goes up, your skip distance starts increasing. Different layers of the ionosphere, and they're miles from Earth. So we have D layer, which is anywhere from 30 to 55 miles. E layer, 60 to 70 miles. F1, 140 miles. F2, 200 miles. The radio horizon is the difference over which two stations can communicate by direct path. So if you're up, let's say 6 feet on an HT, we have the curvature of the Earth. We have another station over here, 6 feet. Each distance is 3.47 miles. You have a combined of 6.94 miles. VHF and UHF radio signals usually travel somewhat farther than a visual line of sight distance between two stations due to the Earth seems less curved to radio waves than light. So VHF tends to hug the Earth a little bit and goes over the curvature of the Earth. UHF tends to go straight through. And this is transmission paths for radio waves, surface waves, space waves, and sky waves, which I covered in the previous slide. Due to UHF frequencies not usually refracted by ionosphere, direct UHF signals are rarely heard from stations outside your local coverage area. It tends to go straight in a line, goes right through the ionosphere, and the curvature of the Earth is going to be your limitation to UHF. Knife-edge diffraction effects might cause radio signals to be heard despite obstructions between transmitting and receiving stations. So if you have like a mountain area, mountain region area, you can still get diffraction. So you can think of it as the radio waves as a garden hose, and if you hit an edge, you can see the waves gets diffracted, or the water would get diffracted off that edge. Tropospheric scatter is responsible for allowing over-the-horizon VHF and UHF communications to ranges approximately 300 miles on a regular basis. This happens a lot, actually. I'm in Massachusetts. I've contacted all the way down to New Jersey and all the way up to New Hampshire using tropospheric scatter. You have pockets of air with different refraction indexes, and it tends to scatter. Temperature inversion. So this is another common thing. This happens a lot, either in the morning or in the evening, where you have some cool and warm air that mix, and this is called tropospheric ducting. And again, I've gone a few hundred miles on VHF because it gets into this duct, and it typically in my area goes north and south. The characteristics of VHF signals received via aurora reflection exhibit rapid fluctuations of strength and often sounds distorted. The 6-meter band is best suited communicating via media scatter. Alright, so auroral VHF, it sounds kind of like a ghosty type transmission. It's in and out. It's very strange. And you really hear a difference when you start getting really north, especially around Alaska area, around Maine. I haven't heard it too much around here in Massachusetts. Media scatter. So we have meteorite